Hello my dear students, welcome back to the fifth session of moving charges and magnetism. In this particular session, we will be taking a look at some of the furtherance of the derivation that we have done. Initially we will take a look at that, and I will give you a small correction that in my previous session that has been incurred. So that correction I will be just showing it to you once again. And after that we will be taking a look at some of the interesting things like direction of magnetic field, how the magnetic field gets acquired in case of a circular coil. Now these all some interesting concepts that we will be seeing, and in the end we will be looking at a line integral concept. Similar to your electrostatics, here we will be introducing a line integral, and with the help of that line integral we'll just take a look at the one of the most interesting laws in moving charges and magnetism, that is Ampere's Circuital law. So that is what we will be dealing with. Now let's move ahead with our first part here. My dear students, in my previous session I had given you some special cases. If you remember, in those special cases, the special case number 3, there was a small correction that I had mentioned during that session, but still I'd like to go ahead with that correction initially. Now, as we can remember or recall back, when point P on the axis is such that x is equal to r, then under this situation we get B is equal to mu naught I r square divided by 2 r square plus r square whole raised to 3 by 2, because x is equal to r here, and accordingly we will get mu naught I r square divided by 2 into 2 r square whole raised to 3 by 2. Then accordingly we will finally obtain it as mu naught I r square divided by 2 raised to 5 by 2 into r cube. So obviously here r square will get cancelled with r cube, and in the denominator we will have mu naught I divided by 2 raised to 5 by 2 into r. In fact, here my dear friends, here I had written by mistake, I had written this as a square. So I hope you can make out this correction. Now without much ado, now let's proceed to our next set of discussion. Now let's take a look at what kind of pattern of magnetic field can be seen in case of a circular coil. That we will just try to understand. My dear friends, if I take a circular coil of this nature, like this, as you all can see on the board. Now here we are considering a circular coil, and this particular circular coil, as you can see, is carrying a current, and there is a cell being connected or battery being connected to this circular coil, and as a matter of fact the current is flowing through this particular circular coil, as you can very easily make this out. Okay, and over here you just need to understand that the current is flowing in this direction, and magnetic lines of force. Now these concentric circles that have been shown in the diagram, these are what? These are the magnetic lines of force, because the circular coil gets magnetically induced, and by the virtue of that there is what? There is magnetic field, and this magnetic field will essentially have what? It will essentially have a magnetic line of force, and that is what has been shown in the diagram. And here in this diagram everything has been marked very neatly, as you can see here. I suggest you kindly draw this diagram. Now accordingly, if we just look at the pattern of magnetic field, how exactly it can be appeared to be seen. Now as you can notice here, initially if I move from the periphery of the circular coil here towards the center, Now at the periphery of the circular coil we have complete circular magnetic lines of force, correct? And when we move away from this particular periphery of the circular coil towards the center, the magnetic lines of force are expanding. As you can see, their radii is increasing. Finally, when it comes to the center, when we observe at the center, magnetic lines of force become straight lines here. I hope you can very easily visualize this, correct? So hence we can say the pattern of magnetic lines of force and pattern of magnetic field, both of them are not fixed in case of circular coil, and we tend to see that the magnetic lines of force give complete circular orientation at the periphery, and they keep on expanding as we move towards the center. Thus, if the magnetic lines of force are varying in radii, then definitely what happens here? Definitely the magnetic field is also varying. This is what we can make out. Hence, we can mention the conclusion as each part of the loop contributes to magnetic field. That is obviously true here. Then magnetic field lines become straight line at the center of the circular coil. So this we have already highlighted, and hence it contributes to maximum magnetic field. And what is that maximum magnetic field, my dear friends? It is obviously, if you just try to understand, it is obviously going to be what? Mu naught I divided by 2R. Remember special case number 1, special case number 2. Okay, in that special case we have derived that expression mu naught I by 2R, that is the maximum magnetic field. I hope this is quite clear. Now let's move ahead with direction of magnetic field. Now direction of magnetic field, it can be noted by using two different methods. Now first method I would like to deal with is right hand thumb rule. Okay, it is also called as right hand fist rule. Okay, so this right hand thumb rule we'll just try to understand now. Method 1, it is right hand thumb rule. Okay, now let us make the statement like this. Imagine that you hold the axis of the coil in the right hand fist in such a way that the fingers are pointing in the direction of the current. Then outstretched thumb gives the direction of the magnetic field. I am certain that, my dear friends, here you would have gotten confused by this long statement. Now let's go ahead and take a look at the same statement diagrammatically. Now I think something is striking in your mind. Now this is a circular coil that we are talking about. Okay, and in this circular coil, at the center we have what? We have straight magnetic lines of force, and these magnetic lines of force straight line, this is passing through the center of the coil. So obviously this is the axis I can call. This is the axial line of this circular coil, and now I'll just show it to you practically by taking hold of one of the circular coil. Now my dear friends, this is the circular coil that I am talking about. Now let me just switch this off so that this coil can be seen very clearly. Now as you can see here, my dear friends, this is the circular coil that I am talking about. This is having n number of turns. Okay, and here I am having the terminals. Okay, these are the terminals. Now these terminals I will be connecting into battery or cell. Okay, so suppose I connect this terminal to the positive terminal of the battery and this terminal to the negative terminal of the battery. Under that situation, definitely the current will start to flow from where? From positive terminal, remember. So obviously current will begin to flow from this particular end. Can you see this particular end? So definitely the current will move in this direction. This is the direction of the current. Now if you just take a look at the statement, okay. Now I am orienting this circular coil just like in the diagram what we are having here. Now, as you can see here, I am orienting this particular circular coil just like this coil in the diagram. Okay. Now, what I will do, I will hold the axis of this particular coil. This is the axis. Can you imagine this? This is the axis. Okay. And at the axis, I am imagining that I am holding the axis like this, such that the fingers are curled. This is the palm. I will be curling my finger like this. I will hold the axis. So that this is the fist, and in the fist I am holding the axis of this circular coil. I hope you are making this out. Okay. Such that curl of the fingers are directed along the current. Now, what is the direction of current here? Direction of current is, this is the positive terminal, so current will flow like this, my dear friends. Current will be flowing from this end, because I told you that I will be connecting this to positive terminal. Suppose, let us imagine that the current is flowing like this. Okay. Under that situation, direction of curl of the finger will be what? Direction of curl of the finger will be like this. Correct? Because current is flowing like this, so I am just curling my fingers like this. So I am holding the axis in this pattern. Okay. Then such that the curl of the fingers are along the current. Then clearly this thumb points the direction of the magnetic field. Now obviously here, as you can notice, this is the curl of the finger. I am holding the axis like this. Then this is the curl of the finger that I am making, and here is the thumb. Thumb is pointing in what direction? In the upward direction. So my dear friends, this is the direction of the magnetic field. Now let me just reverse it. Now let me just hold the coil like this. Now this end is positive, this end is negative. So current will flow in this direction now. Suppose this end is positive, this end is negative. Current will flow in this pattern. Current will flow in this direction now. So under that situation, I will be holding the axis in this way, so that my curl of the fingers will be in the direction of current like this. Then clearly the thumb is pointing downward, my dear friends. Then we can very easily understand that the thumb points the direction of the magnetic field, and direction of the magnetic field in this case is what? Vertically downward. I hope my discussion or explanation is clear to you all. Okay. So this is the same thing. I suggest you take one ring, okay, and try to practice in this way, the way I have shown in the discussion. Now let's proceed to our next part. As you can understand very clearly, this is the diagram that you can draw for this particular statement. Okay, this is a simple diagram that you can draw. Okay, and here is the thumb that we are showing. Now direction of magnetic field is upward. Okay, I hope my discussion regarding this part is clear. Okay, now let's move on to the second method here. Second method number 2, this is called as clock rule. Now in order to make you understand clock rule, okay, you just need to be in a position to understand the direction of current. That's all. Direction of current, if it is clockwise or anti-clockwise, accordingly we can very easily point out the direction of magnetic field. Now before we move any further, my dear friends, I'll just show the direction of magnetic field according to the north pole and south pole firstly. Then we'll just go to this particular statement. Now let's take a look at how the magnetic field lines flow. So that pattern we'll just try to understand. Suppose I'm just going to show you a bar magnet here. Now this is a bar magnet. Now in this bar magnet we have north pole on this side and south pole on this side. And in this bar magnet, always remember that the magnetic field lines or magnetic lines of force, they originate from North Pole and terminate at South Pole. Okay, so they originate from North Pole and terminate at South Pole, and this is outside the magnet. And inside the magnet, what happens here? Inside the magnet, the magnetic lines of force, they originate from South Pole, they move towards the North Pole. So that clearly indicates that the magnetic lines of force are continuous lines and they are not broken lines just like electric lines of force. Okay, so here what is the main factor that you have to remember? Now North Pole will always send out the magnetic field, so that means magnetic lines of force, they come out. That means magnetic lines of force are providing what? Direction to the magnetic field, no? So accordingly we can say that the magnetic lines of force, if they are coming out of North Pole, that means magnetic field is outward. So that means you can very easily understand from the diagram. Suppose we have a coil. Let me just take back that circular coil once again. Suppose we have a coil like this. Now in this particular circular coil, suppose if it is this end, because this is the thickness of the coil what I am talking about, suppose this end is North Pole, then magnetic lines of force will come out of this particular coil like this, no? They come out of the coil surface, this surface, and this end is south. So if we take a look at South Pole, south surface, then magnetic lines of force, they will enter inside the South Pole. So that means if I am observing, your observation point is what? This particular end, no? This surface of the coil. So this surface, if it becomes north, then what should be the direction of magnetic field? It should be towards you. I hope you agree on that. Suppose the surface that you are observing, this surface is South Pole, then the magnetic field will be directed inward, that means away from you. So I hope you can very easily make that out. So here I can talk about that famous Hindi song, Akhiyon se goli mare. I hope you can recall that song, right? So if this is a South Pole, Akhiyon se goli mare, that means your eyes are sending out the magnetic field, and if this surface that you are observing is a North Pole, then your eyes will receive the bullet. That means magnetic field will enter into your eyes. So this is how we can talk about polarity. I hope this polarity concept is clear. Okay, now with this note, now let us move on to the next part of it. Okay, so over here, this is the second method. In this second method, what we will try to do is, we will make the statement like this: if the current through the loop is anti-clockwise, the face of the loop towards the observer is a North Pole. I hope it is clear. It's a very simple statement, right? If the current through the loop is anti-clockwise, then face of the loop towards the observer is North Pole. I hope you can make this out, right? So you can have a look at this diagram now. So current is anti-clockwise, no? As you can notice here, current is anti-clockwise. Okay. So since the current is anti-clockwise, the surface of the coil that you are observing is North Pole. That means magnetic field will come into your eyes. So that means you are taking the bullet. Okay. Akhiyon pe goli mare here. Not akhiyon se goli mare, right? So your eyes will receive that magnetic field. So that is the direction that I am talking about. I hope it is clear. Now second statement, this is statement number 1. Statement number 2, if the current through the loop is clockwise, it should be clockwise, my dear friends. Now let me just make the correction of that. So as you can notice here, if the current through the loop is clockwise, the face of the loop towards the observer is South Pole, as you can very easily notice. And let us take a look at the diagram for this particular respective statement. So here current is clockwise, so as the current is clockwise here, so very clearly the surface that you are observing is south pole. That means you are going to send the magnetic field into the coil. So that is the direction that we are talking about. Remember that Goli effect that I have told you already. Okay, so now let's move on to the next step. So I think in defining the directions of magnetic field, there are two methods that we have discussed, so kindly recall them. Okay, and practice both the methods by taking some circular ring in your home. Definitely you will have at least a bangle of your mother. You take that and try to practice with these approaches, then be thorough in these two methods. Okay, and in the problem solving situation you can use any one of the method. I usually prefer this particular clock rule. This I call as clock rule, and this is one of the best method and easiest technique that we can adapt in case of circular coils. Okay, so now let's move on to the next part, that is how the magnetic field varies. Variation of magnetic field along the axis of the coil. So this is one most important thing. This will be asked in your exam for 1 mark or max to max 2 marks. Now let's take a look at the variation diagram. As you can notice here, the variation is quite predominantly changing kind, and this is not a simple variation. This is definitely a logarithmic or exponential variation on both the sides. But here at the center, as the magnetic lines of force at the center of a particular circular coil are straight lines, as we have already seen. Due to that reason, this is a maximum magnetic field that we can observe. So hence at the center we will have maximum magnetic field, and I'll just place this circular coil here in order to give you that feel. So at the center through the axis we can comfortably see that there is maximum magnetic field, and when we move away from the center, then magnetic field keeps on dropping. I hope this particular approach is clear to you. So I am making the same statement here once again. Magnetic field is maximum at the center and it decreases as we move away from the center on either side of the coil. And what is that maximum magnetic field? It is not, is it not B max is equal to mu naught I by 2R, my friends? So this is already been derived in my previous session. So I hope this particular discussion is clear. Now let's move ahead without much ado. We'll discuss on next part, that is meaning of line integral. Now I think in your day-to-day life, the line integral technique is one of the most important techniques that we can adopt. Okay, now I will be taking some 2 to 3 examples in order to make you understand meaning of line integral first. Okay, firstly I will take one particular approach in case of mechanics. In case of mechanics, if you remember work power energy chapter, do you remember that? I doubt, right? So let us think that you remember work energy power chapter. In that particular chapter, I will be considering one particular situation, as you can notice here. Now here I am taking a block and this is a path. This path I marked it as what? AB, and on this path I am considering a small displacement ds. Okay, here I am applying a force of vector F on this particular block, so that I have to make this block to move on this path. Now this is simple mechanics situation, right? So my dear friends, if I apply a force, will that not provide me a displacement? If that provides a displacement, will it not do a work? So definitely there is a force, there will be a displacement, hence there will be a work. So over here we have a small displacement ds, and we'll assume that throughout this path this object will make such small displacements of magnitude ds throughout the path. Then if I take the integration of this entire process, that is what line integral, because I am moving through this path now. So line integral means, line means not a straight line, we are talking about what? Path here. So that is what we have. So hence, let's take a look at that same situation what I have explained. Work dW can be calculated, a small amount of work in moving this object for a small displacement ds. Now, that can be written very easily as what? Vector f dot vector ds, it's a scalar product. Okay, so accordingly we'll get WAB, that is the total work done in moving the object from A to B, will be what? Integral from A to B vector f dot vector ds, and over here at point A we have one position vector, at point B we have second position vector. In between these two position vectors we have change in position, and that change in position will provide me what? Net displacement. That is why we are using what? Integration here. I hope this particular approach is clear to you. So what is line integral, my friends? Line integral is nothing but it is the amount of work done in moving an object from one position to another position over that entire path. So that is line integral in case of mechanics. Now let's take a look at electrostatics. I think this you should not have forgotten, because very recently this part has been covered to you people. Okay, so this is the statement once again I am making for the sake of you people writing it down. Okay, now in case of electrostatics, now if you consider a charge say plus q, now this charge plus q I want to move it to B here. Then under this situation, in doing so I am making small displacement of say dr. Then very clearly we can see that the net amount of work done in bringing a unit charge from A to B, what it is called as? I am just waiting. It is called as what? Potential difference. So that potential difference we are just calculating in case of electrostatics. In order to calculate potential difference, my dear friends, we require again line integral, and let us go to that mathematical calculation here. So we know that electric field is a negative potential gradient. This derivation you would have done already. So hence I can write this as E is equal to minus dV by dr. Okay, so over here, therefore potential difference will become what? Here we know that dr is nothing but a displacement vector. Okay, and E is nothing but a electric field vector, and these two will have a scalar product to give a scalar quantity of potential difference. So very clearly we have minus of vector E dot vector dr, and this is the potential difference. My dear friends, I think I need to make this as a dV instead of V, then it will be much clear to you. So we can very easily take this as a dV. So let me just make it as a dV here first. So this is dV is equal to, so this is the, so this is the electric potential for that small displacement dr. That is what we are making here. So now let's go to that particular same equation here. As you can notice, we have vector E dot dr is small potential difference or potential difference between that initial point and a small displacement point at a distance of dr. Then total potential difference over the closed path AB will be what? Closed path AB will be very clearly integral from A to B E dot dr. So this is again a line integral. So line integral of electric field vector and displacement vector is nothing but potential difference. In case of electrostatics, it is the same statement that I am making out here for the sake of your clarity. So I hope the meaning of line integral is clear to you. Now in case of magnetism, again we have a line integral, and that line integral is the line integral of magnetic field with respect to the displacement again. So that is what we are going to see as one of the laws, and in that law we will be making use of this line integral of magnetic field. Okay, so quick rehearsal. What is line integral of electric field? It is called as potential difference. Line integral of force is nothing but work done. So similarly, line integral of magnetic field is equal to what? That is what we are going to see in our next part. Let us move ahead now. Now this particular law, it is called as Ampere's Circuital law. This is one of the backbone law for this particular magnetostatics and magnetodynamics concepts. Okay, and for this moving charges magnetism, my friends, it is just like your Gauss law in case of electrostatics. It is just similar to that, whereas in case of Gauss law we had static charges, here we have moving charges. That's all. That is the difference. Okay, now let's take a look at that particular statement. The statement of this law is very simple. It states the line integral of magnetic field vector B around any closed path in vacuum or in air is equal to mu naught times the current enclosed by that path. So is it not one of the cakewalk statement that you can make out? So it's very simple. Line integral of magnetic field vector B around any closed path in vacuum or air is equal to what? Mu naught times the current. Current is what? Capital I. So I can very simply write this as what? Line integral of vector B dot dl is equal to mu naught into I. So line integral of magnetic field is this one, my friends. Vector B dot vector dl we have written now. Just like previous case, over there we had vector E dot vector dr. Just like that, here we have vector B dot vector dl. That is the line integral, and this line integral is nothing but what? Mu naught into I. So it is analogous to your potential difference or work done in case of mechanics and electrostatics respectively. But unlike them, it is not exactly having the same meaning, my dear friends. Mu naught into I, that means in case of moving charges and magnetism, due to the moving charges, that means whenever current flows through a conductor, we have what? Magnetic effect, and hence instead of charge we have what? We have current here. So because of that reason, we have mu naught into I, and this is going to provide me what? This is going to provide me the ability of that particular coil to provide a required magnetic field. How much magnetic field it can provide? Suppose if it carries a current of I. This is one simple statement that we can understand as. Okay, I hope this is clear. So now what each of them are, that is what I am mentioning. Again, integral of vector B dot vector dl is the line integral of magnetic field vector B around the closed path, and I is the electric current enclosed by that closed path. Now what is a closed path? You must be wondering, what is closed path? Closed path is just like the circular coil that I have discussed already. Now this is a circular coil. This is again a closed path. No? Here we don't have any openings here. So hence I can call this ring as not a closed path. Similarly, I can take one rectangular coil. In that rectangular coil again we have what? Closed path. So that is a closed path, just like this notebook. Suppose this notebook I consider as a rectangular coil. There is no opening here, so we can comfortably call this as what? A closed path. So it is closed path means, my dear friends, it is like a closed area. Like in case of electrostatics we have had, no? So remember that. Okay, so like that. So accordingly, let us move on to the proof of Ampere's circuital law. But prior to that, let me just make a quick reflex on where and how this particular law can be utilized and where it is applicable. That we'll just try to understand. This particular statement, it holds true irrespective of shape and size of the closed path. As I was explaining to you earlier, circular closed path, square closed path, it can be any particular shape. Okay. So irrespective of shape and size, this law can be very easily applied. Second point we should remember is the law holds true for steady currents only. So this particular thing, my dear friends, if we have varying current, then this law fails to be applied. So remember that this these 2 points that I have mentioned, these 2 points can be asked in your examination as give any two points upon which Ampere circuital law holds true. This is a standard 2-mark question in your exam, so that is why I am mentioning this. So kindly note this down and remember this. Now let's move on to the next part, that is proof of Ampere circuital law. Now in order to prove this Ampere circuital law, we need to make one simple diagram. That diagram we can draw like this. I am considering one circular loop, okay, and this circular loop what I have drawn, this is not circular coil, my dear friends. Here firstly I will be considering one straight conductor, okay, and this straight conductor is carrying a current I here. Fine, that is what I have shown in the diagram as well. And around this straight conductor I am considering one particular loop, circular loop. Now this is just like your Gaussian surface. Here we call this as Amperian surface. In case of electrostatics, you have drawn Gaussian surfaces, remember. But here in moving charges and magnetism, we will be drawing what? Amperian surface like this. And that particular thing I will be stating a bit later. Now kindly make a note of this diagram. And here we will say consider a long straight conductor, as I was mentioning to you earlier. Let capital I be the current carried by the conductor. Then I will consider a circular magnetic line of force. Magnetic line of force I am mentioning in order to not to make you people get confused. This is nothing but Amperian surface only, but here I am writing it as what? Magnetic line of force, because in case of a straight conductor carrying current, we will always have magnetic line of force as concentric circular lines. So accordingly I am considering one such magnetic line of force having a radius of small r, okay, and here conductor is obviously passing through the center of this magnetic line of force. Now let's proceed to the next consideration. Consider an element dl here. So I am considering a small element dl, and this dl business I think you are perfect by now, okay. We have already made use of this element dl n number of times. I think now it is quite clear to you all. Hence now let's proceed to the next step into the derivation. For our reference I am keeping this particular diagram. Now on this closed path, magnitude of magnetic field is same everywhere, because we know that circle has a property that its radius is same. So circle will not have varying radius, no? Because of that reason, the position on this particular circular path, you take any particular position, at every single position on this circular path, magnetic field will be what? Same magnitude. It will have same magnitude, because this particular point what you are saying, this point is separated at the same distance from the straight wire. So because of that reason, we can say that magnitude of the magnetic field is same everywhere. Then also B acts along the tangent to this closed path, and vector dl also acts along this particular path, okay. So dl is element, and element vector dl, it will have same direction as vector b. So that means angle between b and dl is 0 degree here. So because of that reason, why am I using this? Because we are using this in the line integral, and in the line integral we have what? We have dot product. In the dot product we will always have cos theta. Remember that theta value will be 0 here. So hence in that cos theta I will be putting it directly as 1 in my derivation step. So over here I will consider firstly integral of vector b dot dl is equal to line integral of b into dl. Now what is dot product? Integral b dot dl is equal to magnitude of b into magnitude of dl into cos theta, and theta is what here? Theta is 0. Because of that reason, in this particular part I am saying cos 0 is equal to 1, and that 1 has been multiplied with b and dl. So accordingly we have integral of b into dl here. So this is a very simple thing. It is not a rocket science. You can very easily understand this, right? So now let's move on to the next step. So here magnetic field is same. Here I already mentioned that magnitude of magnetic field is same. That means B is constant here. So hence this B has been brought out of the integral here. So hence inside the integral we have what? dl. So integral of dl is nothing but what? What is the total sum of all the dl's if I add? Will it not give the circular path? So that means circumference, no? So what is circumference of circle? Circumference of circle is 2 pi r. So hence we have what? B into 2 pi r here. Now over here we have next step. Magnetic field due to a straight conductor carrying current is given by B is equal to mu naught I by 2 pi r. So this is the magnetic field value that you should remember. Mu naught I by 2 pi r is the magnetic field due to a straight conductor carrying current. Fine. So this is the formula that I am utilizing here. Thus accordingly, integral of vector B dot vector dl is equal to B into 2 pi r. Then we have mu naught I by 2 pi r into 2 pi r here. So accordingly 2 pi r and 2 pi r they get cancelled over here. Now these two will get cancelled and accordingly we will get mu naught into I. Now this is the statement that we have already. Remember, line integral of magnetic field is the product of mu naught into I. This is what we had stated and thus we have proved it. So I hope this particular part of discussion is clear to you all. So in my next part I will be taking a look at applications of Ampere's circuital law. I hope this part is clear to you all. I'll proceed to my closure of this topic. I hope this part is very much clear to you all. Thank you so much. Have a nice time. So I'll be seeing you soon with my next session in a quick succession of time. Thank you very much. Have a nice time.